So now we're going to change this, change a little on the subject. Now we're going to look at noise. Noise in our system, electromagnetic noise, that you get into a system, a little about how you can remove it using software. This is again just for information on noise. Let's say we'll move over here. So what is noise? We have got a signal. It's a nice deterministic sine signal. We have got some random noise on it, and this is what we end up with, and we want to get rid of this noise. So okay, there are types of noise. They say we call it by color. We know white noise, all frequency is in the noise, brown noise, low frequency, and blue noise, high frequencies. Should be colors on here too, but it's kind of like this is uniform. There's a low noises that has everything you can't even distinguish the noise. I pick the noise out here. Where does this noise come from? That's internal, what you call Thurman-Johnson noise, caused by random electron movement due to changes in temperature, which we always have. And they're moving around, and these fields are moving around and influencing you. And then we have external noise sources, which are power sources, light sources, radio transmitter, generators, switching devices, whatever. But you are devices from coils and discharge of capacitors and let's say power the power nodes and stuff. What this one shows here, just when you switch on a coil, you have a freewheeling diode to make sure that your noise here, at least this pulse, is not being returned to your system, so you have to get rid of it. So this is one way that you probably should get rid of noise on coils that you're controlling now. So how do we get it? It's induced, which is an electrical magnetic field that's kind of influencing your wire here, you know, and getting the electrons to move in your wire, and that's going to turn up like noise in your load here too. So that was the electric field, and here we've got the magnetic field too, the coupling too here. So capacitive here and inductive. Capacitive, of course, it's an electric field, and inductive, you know, then you have coils interacting here too. And then you have induced noise, earth potential differential too. That noise is communicating here, down here. You're pretty good up here, but you get noise through this stuff. And then we've got these earth loops too. This also can change the signal too. But then also we have an earth loop here that's kind of circulating currents, and that's inducing current in one of your signal loops here, and that's not too good either. So that's also the reason why you should earth it in only one location to prevent these earth loops too. Noise reduction external, physical separation, it was power, signal, twisted pair wires, because then let's say a special electromagnetic noise, it's going to induce a voltage on one cable, but they are twisted, so you get the same voltage on both cables basically here. For induced too, and then there's also the capacitance that's kind of evened out too. Wire crossing at 90 degrees, that's for the magnetic fields. We don't have parallel wires, we cross them, and then the magnetic field is not going to induce anything or much in that wire. And then we have got shielding for electromagnetic field. That's the principle of, let's say, the Faraday cages too. That okay, no matter what kind of electric field you have on the outside, you don't get anything on the inside. So here is some cable, as a cable. I think this is from, you might not find this figure anymore. But here we have maybe twisted pairs, and we have individual shields. We have drain wires, which drain whatever electrons are in, we drain them down to ground somewhere. And this is just plastic, armor is just for the strength, and so on. Okay, capacitive coupling, again, physical separation, Faraday cages, okay, whatever field we have on the outside here, we don't have any disturbance inside. That's kind of nice. And balancing inductance too here. So line carrying interfering signals, you know, it's cold and hot. So we have both our signals over here too, so you can do things like this. I think this is from National Instrument or something. I found this. Safety earth, this has a little to do with earth and grounding. Safety earth, that's so you don't get killed when you touch a wire. Signal ground is so we don't get noise into a system. Then we have high frequency bounding, because this high frequency, they are going to jump between your wires. Because high frequency, they see all kind of separation. You have plastic or whatever. You say, okay, I'm high frequency, so all the capacitors I'm looking at, they are short circuits to me. I'm going to jump into those. But what we are going to do is that we're going to use braids and say, okay, before you get into my system, we are going to pass you down to ground, get rid of you. So this is chassis ground to high frequency grounding. And here is also the grounding too. And here maybe you should have only ground in one location here. Maybe this one shouldn't be grounded. Then get rid of the noise. We have low pass filters. Let the green one through. High pass filter, the green will go through, the low pass doesn't pass. Band pass, a portion of the frequency will let through, and band stop, low and high frequencies get through. Most of what we're looking at, the noise is high frequency most often, so this is the normal low pass filtering is important. Here are some quick ways of removing, let's say, low pass or high frequency noise. Here, just take an average of the noise and you get a straight line out of this. This is going to average out of the time. Next one, way back in time. So then you have got, let's say, a moving average filter here. I get new measurement in and the old one, they even out. This filter, you look at, let's say, the signal you have and say, okay, if I even this signal out over this time period, how often I want to update my signal, I don't care, but over this time period, I'm going to even the signal out. And then my noise disappears, because clearly this is noise. It might not be, but it can be. But if it is, then this should be removed, and it is the average here, pretty much that is the signal I am looking for. And the formula here is awfully simple. So here's some pseudocode. It's not a FIR filter or moving average filter. If it was a FIR filter, then we would need a weight on each of these inputs we read. So, but it is a special type of FIR filter, finite impulse response filter, which because says, okay, an impulse is going to die out over time. Yeah. But then again, for each of the individuals, that is one. They have the equal weight, all of them. So here's just how you could do this. Some roll down a FIFO and then calculate an average or something like this. Pseudocode. And then also a popular filter is a first order butterworth low pass filter. They're more popular as a second order one. But here you can use, this is the Laplace transform, where this is cutoff frequency. You use the bilinear transformation or Thurston or whatever you call it for the S here and do a calculation. You end up with this, discrete equation where these are known. Sampling time and cutoff frequency is something you specified. And here is, let's say, a way of programming the filter or something. Easy. It's fairly easy to implement a filter like this. Remember, they are recursive. You call it once, and then you have this k-1, which was the last value, and then you call it another time after a sampling period and do a new calculation, get a new k-1, and so on. So these are, then they call, this is something we call and then an infinite impulse response filter, because here we are always based on the old signal that we calculate, and that is never going to turn to zero in theory. But of course the numeric resolution of your CPU, if it's 32-bit or something, is going eventually to die out, because you can't represent the small numbers. It's going eventually to die out. And in theory, it's never going to die out. So we looked at two here: finite impulse or moving average filter, which is a special case for the finite impulse response. And here's an infinite impulse response filter. That's a better filter. And that saves old calculated values. It depends on what I did calculate the last time for this one. Yeah, so that was a little about noise sources, induced noise, electromagnetic noise, and how to get it in, and earth loops, and how to physical separate, do 90-degree crossing and so on, and then looked at a little noise removal in software, but there are also analog filters, so we get rid of the noise before we get it into a controller, which might often be nice, and if there's awfully high speed noise, then we would need a special DSP, digital signal process, to execute these filters, and a normal, let's say, automation device won't be able to do this, and then we could use an external, let's say, a passive filter or an active filter or whatever, but an external filter that's not a part of the PLC program. Program, or a filter that you have programmed, or a library with filters that you have been using.